I want to introduce a new concept known as the intensity reflection coefficient. Intensity reflection coefficient. What is it all about? Well, you can have the ratio of the reflected wave to the incident, right? Not necessarily incident transmitted wave, but just the incident wave itself. Because if I say incident transmitted wave, you're going to be confused if you see incident and transmitted close together, okay? So you want to find a ratio that tells you how much has been reflected or how much has been absorbed. You want a number to quantify that. You're going to have what we call the intensity reflection coefficient. Now, this will help us identify whether or not we don't lose all of the ultrasound due to reflection. So the intensity reflection coefficient is essentially like what I'm saying, the ratio of the intensity of the reflected wave, which is over here, to the ratio of the wave that is incident, which is over there. And we have a way in which we can be able to relate those ratios, the coefficient itself to specific acoustic impedances. So we can say Z2 minus Z1. So if you're given two mediums, one with specific acoustic impedance Z2 and the other with Z1, you can therefore be able to say Z2 minus Z1 divided by Z2 plus Z1, all of that squared. So what you're getting is what's known as the intensity reflection coefficient, which is a ratio that's telling you that, so the ratio lies between 0 and 1. Right? It doesn't have a dimension. So if you're close to 1, it implies that almost all the wave was reflected. If you're close to 0, it implies very few of the wave was reflected. Most of it was actually transmitted. So that's why we need such a ratio that quantifies how much of the wave has been reflected. Because we can know then, because we're very interested in the wave that has been reflected. Okay, so this is the mathematical equation that is used to calculate specific acoustic impedances. Don't worry yourself too much about understanding where it comes from. Please don't. I've tried. The calculations can be a bit advanced and a bit complicated. You have to read into pressure continuity, velocity continuity, a whole lot of stuff that are a bit unnecessary. But essentially, this mathematical equation that you have above can be used to calculate this coefficient, Z2 minus Z1 over Z2 plus Z1, all of that squared. Just memorize that in your head and you should be fine. So if there's a large difference between specific acoustic impedances of material, then most of the energy will be reflected. If it's near to 1, that implies most of the wave is reflected. If there's a small difference between acoustic impedances, then the IRC will be close to 0, if not 0, and most of the wave will not be reflected. What do I mean by this? Remember, I said that my intensity reflection coefficient alpha is essentially equal to Z2 minus Z1 over Z2 plus Z1, all of that squared. Okay? So you can think of this as if you have one material, if you have material A and material B, then the Z for this is equal to 20. Then the Z for this is equal to 21, let's say. Okay, so at the top you're going to have 21 minus 20 divided by 21 plus 20, all of that squared. Okay, that's going to be 1 over 42, which is a very, very small number. All of that squared, right, which is 1 squared over 42 squared. This number is nearly close to 0. And what that tells you is that if the acoustic impedances are very similar, if this value and this value are very similar in magnitude, you're going to get most of the wave passing through and very few of the waves being reflected. If I go here, I hope it's making sense. If I say I have, again, medium A and medium B, then for this one, the value of Z is actually equal to, give or take, 20. Then for this one, the value of Z is equal to, give or take, 5. Right? You're going to go on top and say 20 minus 5 divided by 20 plus 5. All of that squared. 20 minus 5, that's 15. 20 plus 5, that's 25. You get more than 0.5 actually. So that implies more than half of the wave will be reflected. And I'm seeing that because the acoustic impedances are very different. Right? So that's what I'm saying. If there's a large difference between the acoustic impedances, most of the wave will be reflected. If there's a very low difference between the acoustic impedances, most of the waves will be transmitted. Okay. So this is what we mean by intensity reflection coefficient. In the next video, we're going to look at a couple of examples underneath this concept. And remember, all you need to understand is that we're looking for a way to quantify how much of the waves can actually be reflected. The ratio lies from 0 all the way to 1. If you're very close to 0, it implies that very few of the wave is actually reflected, most of it transmits. And that only occurs when the acoustic impedances are very similar. And if the ratio is nearer to 1, that implies nearly all of the waves are going to be reflected. And what this therefore means is that one of the acoustic impedances is actually greater than the acoustic impedances of the other wave. And that will be all.